Welcome to Session 6 of Digital Basics, Part 1 of the Digital Design series. As usual, we begin by reviewing the answers from last session's exercises. For the first exercise, we're asked to convert some binary numbers to their 2's complement version. Starting with the first one, we take the 1's complement, and from that we add 1 to get the 2's complement answer. From here, we're going to explore some perimeter values that we might encounter as we convert 2's complements. Starting with a simple one, we again find the 1's complement, this time with a larger bit field, and then the 2's complement. So we see that a -1 is all ones. It can take some getting used to. A number that offhand seems very large is actually the smallest it can be, other than 0. And speaking of which, we find that the 2's complement of 0 is 0, a unique case. A -0 is the same as a +0, which more or less makes sense as neither has the actual quantity to complement. But what about a true -0, a 0 with a negative sign bit? We find the 1's complement, and then find that the 2's complement takes us back to where we started. So we effectively have 2 -0s. Finally, we start with a negative value that's all ones and find that the 2's complement is a +1. But we already knew that. Next, we'll exercise our negative arithmetic muscles. We find the 2's complement of 4. At this point, we'll skip the 1's complement conversion, since that's probably second nature by now. We add the 2's complement of 4 to 7 and get 3, as we expect. Next, we're adding 2 negative numbers. But first, we note that a +12 requires 4 bits. So we need to expand the bit field to accommodate a sign bit. We find the 2's complement of 12, and then the 2's complement of 3. Adding them, we get this. And we see from the MS bit that it's a negative value. So we do the 2's complement conversion and find that, happily, it's a -15. For the last one, we've already done the 2's complement conversion of -12, and we see that subtracting a -3 is the same as adding a +3, and a 2's complement conversion yields a -9, what we expect from 12 minus 3. We begin this session with binary multiplication, and we're going to find it pretty straightforward. Let's take a binary 4 multiplied by a binary 3. Note that we're leaving one MS bit position reserved for negative values. We perform binary multiplication just as we would with our old-fashioned decimal version. In fact, it's even easier, since when we multiply the first digit of the multiplier, the bottom one, against the complete multiplicand, the top one, since binary includes just 0 or 1, then we either pull down the multiplicand if the multiplier digit is 1, or we don't if it's 0. Proceeding on, again, just as old-style multiplication, we pull down the complete multiplicand, shifting to the left. And then we add. And no surprise, we get the right answer. Note that we need to expand the bit field to accommodate the larger results. Next, we'll look at a special case of binary multiplication. Here, we're multiplying 5 by 2. And so we carry down the multiplicand, shifting to the left as we go. But we pause to look at this. We multiplied by 2 and shifted the multiplicand left one place. We see that when we multiply by 4, again it's the multiplicand, but now shifted 2 places. In fact, each binary bit location of the multiplier is another left shift of the multiplicand. Thus, the bit position of the multiplier determines the shift location of the multiplicand in the answer. Of course, this only works when there's just one bit asserted in the multiplier, by 2, by 4, by 8, and so on. We've been multiplying positive numbers, but what about negative ones? Again, it's the same procedure we would use for decimal numbers. We first convert all the numbers positive, go ahead and do the multiplication, and finally count up the number of negative ones. If there's an odd number, then we know that the answer is negative, and if so, we convert it to 2's complement. We next take a look at a very useful little trick that Mr. De Morgan found over 100 years ago and now named after him. Take an AND gate. De Morgan's theorem states that this is equivalent to an OR gate with inverted inputs and outputs. The general rule is first change the logic type and then invert all inputs and the output. We can demonstrate this with our trusty truth table. Here's the table for the AND gate. And this is the table for the inverted OR, where any 0 input makes the OR gate active, but the inversion at the output results in a 0 out. Only when both inputs are a 1, when the OR gate is now inactive, does the output go to a 1. And so, we see that the truth tables are identical. The same thing applies going the other way. The principle applies also with other types of inversions. Given this OR gate with an inverter at one input, the resulting De Morgan equivalent AND gate has that input not inverted. We're now going to take another fundamental step forward in our discovery of digital logic operations. Here we have just 2 AND gates with inverted inputs, and we've wrapped the outputs back on themselves, what we could call feedback. As we'll see, this arrangement has a very important feature. We'll begin our analysis by assuming that both input signals are low. Further, we'll assume, just to start, that the output of the lower AND gate is low, which enables the upper AND gate. And since sig A is low, the upper AND gate's output is therefore high. That high at the lower AND gate forces its output low, and we're back where we started. What this means is that we have a stable relationship of the interconnected gates. Now though, let's make sig A go high. That forces the top gate to go low. And since sig B is still low, the lower gate goes high. And that high forces the upper gate low, so that even if sig A goes back low, the upper gate stays low. So we started with a stable configuration, and by toggling sig A high and then low again, we completely reversed the new stable states of the gates. You can see that if we now toggled sig B high, we would revert back to the original stable states. We could call this gate configuration a latch, since it latches or holds the states of inputs presented to it. Let's take one of the gates, say the lower one, and call it the output. In that case, we could change the name of sig A to set, since it sets the output high. Similarly, we could rename sig B clear, since it clears the output low. And here's the exercises for this session, session 6. Since this is the last session for this part, the answers will be in their own dedicated video.